Hello everyone. I'm going to go through the DFS and BFS examples from the workbook that I gave you on Monday. Please excuse the paper and pencil situation today. I do have a graphics tablet on the way, my old one broke, so my future videos will be on the computer, hopefully be a bit better than this one. Okay, so DFS first. Now it would be good if you were looking at the algorithm at the same time so you can follow what I'm doing. And I'd also like to point out that there can be, in terms of the order of the nodes that you get after running this algorithm, there can be varying answers, and that's all because it depends on which of the children you take first. So when you implement this, you would have a particular rule. You'd either follow numerically or you'd always take the left child first. And in this video, I'm going to be taking the left children. I'm going to go from the left when I choose the children. Okay, so let's start following the algorithm. Mark the starting node of the graph as visited and push it onto the stack. So I'm going to start on 1. Make that decision at the beginning. So mark 1 as visited and push it onto the stack. While the stack is not empty, it is not, peek at the top node of the stack. So when we're peeking, we're not removing it, we're just looking at it. If there is an unvisited child of the node, mark that child as visited and push the child node onto the stack. So we're looking at 1, we've got 2 unvisited children because neither 2 or 5 are in our visited list. And as I said, we're going to choose to take the left child first, so that would be 5. So 5 now goes into the visited list and we push 5 onto the stack. So now we're going back through the while loop here. So while the stack is not empty, peek at the top of the node. So now we're looking at 5. If there is an unvisited child, so we're looking at 5's children, we've got 2 and we've got 4. So again, choose left child first, so that's 4. So we're adding 4, or marking 4 as visited, and adding 4 to the stack. Again, peeking at the top of the stack, looking at 4 now. Unvisited children, choosing left children first, would be 6. So you can see why this is called depth first, because it's, if we think about how far we are away from our starting node as we go, we're immediately going into the next layer away from our starting node every time we choose a new child. Okay, so now we're as deep as we can go when we get to 6. So we're marking 6 as visited, pushing 6 onto the stack. There we go. Going back through the while loop, stack's not empty, peek at node 6. 6 does not have any children that are unvisited because 4's already been visited and that's its only child. So we're going to the else, pop the top node off the stack. So we're just left with 154. Nothing changes in the visited list this time. Again, peek again, 4. 4 does have an unvisited child, that's 3. So 3 is now going to be added to our visited and put at the top of the stack. Now we peek at 3, has an unvisited child, 2. So 1, 5, 4, 6, 3, and then 2 is the last one to be marked as visited. And in the stack, we add 2. Now what's going to happen is every time we go through the while loop and we peek at the top node, we're going to discover that there are no unvisited children because everything in the graph is now visited. So we're just going to keep popping the top off. So I've stopped here because it's going to just carry on 1, 5, 1, 5, 4, 1 until your stack is empty. And then once your stack is empty, the while loop no longer triggers and you are done with your depth first search. Okay, so you can see we have the order of nodes visited here, goes in deep before it goes for breadth, which is what the other algorithm goes for. Note that if we were to do numerical order instead of left child node, we would have actually gone for 2 next in the visited list. So like I said earlier, you can get different outcomes, but if you implement it in code, then you should always get the same outcome for the same graph. It's just depending on how you choose your child nodes. Okay, so that's depth first done. Let's have a look at breadth first now. So different setup this time. We've got a queue, so I've written it horizontally rather than vertically. Makes more sense for a queue. And again, be looking at the algorithm so you can follow it with me. Okay, mark the start. Okay, I'm going to start with 1 again, sorry. Mark the starting node of the graph as visited and enqueue it into the queue. So starting node be 1. Sorry, I was just checking something. And Q1 visited 1. Okay, while the queue is not empty, dequeue the next node from the queue to become the current node. Okay, I should not have put 1 as a current node there, sorry, I have to get rid of that. While there is an unvisited child of the current node, mark the child as visited and enqueue the child node into the queue. So we're looking at node 1 and there are 2 unvisited children. So we're going to keep going until we've covered all of the children of the first node. So you can see we're staying in that first level before moving any deeper into the graph. So we'll go with the same thing as before, choosing the left child first. So we're going to queue, so this time it goes to the back of the queue, 5 and mark it as visited. And then still got 1 as our current node. And we're going to, oh wait, hold on a minute. We did not dequeue 1. Sorry about this. We just got 5 in our queue right now. So 5, but we do add 2 to our queue here, and it goes onto our visited list. Okay, so this is while there is unvisited children. So at the moment, our current node 1, we no longer have unvisited children because both 5 and 2 are now in our visited list. That while loop will not, the inner while loop will not be called anymore. Now on the outer while loop, the queue is not empty. Dequeue the next node, which is 5. So we've just got 2 now. And do the while there's an unvisited child. So for 5, we've got just 4. So we add 4 to our visited and 4 gets put in the queue. There's no more, let's just mark that as visited, no more unvisited children of 5. So now we're going to come back to the queue and dequeue the next item in the queue, leaving just 4. So now we're coming back over to 2. 2 has 1 unvisited child, which is 3. So we'll add that to the visited list now and put it at the back of the queue. No more unvisited children of 2. So now again, we dequeue the next node, which is 4. I realise I need to shade that in. So now we're focusing on 4. We've got 3 left in the queue because we dequeued 4. And we have 1 unvisited child, which we will place. So 6 is now the last node to be visited because it's the furthest away from our starting node. It's the deepest into the graph. And we are going to queue it. And then we take 3 into our current node and 6 is left in the queue. Our visited does not change. We know it won't now because it's got all the nodes in it. And then that just leaves us, well, there's nothing to do with 3 as the current node because there is no unvisited children of 3. Meaning we just dequeue 6. Don't change our visited list. And then we are finished because the queue is now empty. So the first while loop does not trigger. Okay, so I hope that you found that helpful in understanding how BFS and DFS work. The way that these are likely to be implemented in the exam would be via an algorithm that you would have to trace in a trace table, I'm afraid. But we will be doing some exam questions very soon to practice using this algorithm. Okay, well, I will see you either in the next video or possibly in some kind of Google Meet or Zoom meeting. I haven't quite got around to thinking ahead on that yet. But either way, I hope to see or hear from you all very soon. Take care, everyone.